Tonight, we're going to talk about the moon. And I know what you're thinking. We've been there. We planted flags, we collected rocks, and we came home. So why are we going back? Here's what most people don't realize. The reason we're returning to the moon has almost nothing to do with national pride or political ambition. The real reasons are buried in physics. In orbital mechanics that make the moon the most strategic location any civilization could hope for. In 4.5 billion years of untouched geological records sitting on its surface right now. In the fact that the far side of the moon is the quietest place in the entire solar system. And in a simple, stunning truth, if humanity ever wants to go anywhere else, the moon isn't optional, it's mandatory. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, make yourself comfortable and let's begin. Let's start with something that most people never think about, but that controls everything about space travel. Gravity. Not in the vague sense of things falling down, but in the precise, mathematical, unforgiving sense that determines whether a rocket reaches orbit or falls back to Earth in a fireball. Because here's the truth that changes everything about why we're going back to the moon. The single hardest thing any space mission ever does, the part that costs the most energy, the most fuel, and the most money is the first step, getting off Earth. Think about it this way. Imagine you're standing at the bottom of a well. Not a small well you could climb out of with a ladder, but a deep well. A well so deep that climbing out of it requires more effort than walking 1,000 miles across flat ground once you're at the top. That's what Earth's gravity is. A well. Physicists actually call it a gravity well, and it's one of the most important concepts in all of spaceflight. Earth has a mass of about 5.97 trillion kilograms. That's a 5 followed by 24 zeros. All of that mass is pulling everything on the surface toward the center of the planet. To escape that pull, to break free of Earth's gravity completely, you need to reach a speed of about 11.2 kilometers per second. That's roughly 25,000 miles per hour. This is called escape velocity, and it's non-negotiable. Physics doesn't care about your budget or your schedule. If you don't reach that speed, you're not leaving. But here's where it gets interesting. You don't actually need to reach full escape velocity just to get into orbit. To reach low Earth orbit, which is about 160 to 2,000 kilometers above the surface, you need to accelerate to roughly 7.8 kilometers per second. That's about 17,500 miles per hour. And achieving that velocity requires an enormous amount of energy. This is where a concept called delta V becomes essential. Delta V is the total change in velocity a spacecraft needs to perform a maneuver. Think of it as a budget, except instead of dollars, you're spending speed. Every maneuver in space, every orbit change, every landing, every launch costs a certain amount of delta V, and you pay for delta V with fuel. The more delta V you need, the more fuel you carry. The more fuel you carry, the heavier your rocket. The heavier your rocket, the more fuel you need just to lift the fuel. It's a vicious circle that rocket scientists call the tyranny of the rocket equation. The man who first described this equation was Konstantin Tsiolkovsky, a Russian scientist working in the late 1800s. His equation shows that the relationship between fuel and payload is exponential, not linear. This means that if you want to go a little bit farther or a little bit faster, you don't need a little more fuel. You need a lot more fuel. Sometimes drastically more. This is why rockets are mostly fuel. The Saturn V rocket that took Apollo astronauts to the moon was more than 90% fuel by mass. The actual spacecraft, the part with the astronauts and the equipment and everything they needed, was a tiny fraction sitting on top of an enormous tower of propellant. Now, here's the fact that changes how you should think about space exploration. Getting from the surface of Earth to low Earth orbit costs about 9.4 kilometers per second of delta V. Getting from low Earth orbit to the surface of the moon costs about 6 kilometers per second. Read those numbers again. The trip from the ground to orbit, a distance of maybe 300 kilometers, costs more delta V than the trip from orbit to the moon, a distance of roughly 384,000 kilometers. The first 300 kilometers are harder than the next 384,000. There's a famous saying in aerospace that was inspired by the science fiction writer Robert Heinlein. Once you're in orbit, you're halfway to anywhere. And it's essentially true. The overwhelming majority of the energy required for any space mission is spent in those first few minutes of flight, clawing up through the atmosphere against the relentless pull of Earth's gravity. Once you've made it to orbit, the rest of the solar system becomes surprisingly accessible, because in the vacuum of space, with no air resistance and no friction, you can coast. A little push goes a very long way, and this is where the moon enters the picture. Not as a destination, but as a strategic location. The most strategically important piece of real estate in the entire solar system. The moon sits about 384,000 kilometers from Earth. In cosmic terms, that's nothing. Light covers that distance in about 1.3 seconds. A spacecraft can reach the moon in about 3 days. Compare that to Mars, which takes 7 to 9 months, or Jupiter, which takes years. The moon is right there. It's close enough to reach quickly, close enough to communicate with in near real time, and close enough to abort and return home within a week if something goes wrong. But proximity isn't what makes the moon special. What makes the moon special is its gravity well, or rather how shallow that well is. The moon's surface gravity is about 1/6 of Earth's. If you weigh 180 pounds on Earth, you weigh about 30 pounds on the moon. This isn't just a fun fact for astronauts bouncing around in spacesuits. It's a game-changing advantage for spaceflight. Because a shallow gravity well means you need far less energy to launch from the surface. Far less fuel, far less cost. The escape velocity from the moon is only about 2.4 kilometers per second, compared to Earth's 11.2. That's nearly 5 times less. Let me put this in practical terms. To launch a spacecraft from Earth's surface into orbit requires a massive multi-stage rocket burning millions of pounds of propellant. To launch the same spacecraft from the moon's surface, you'd need a vehicle that looks more like a large car than a skyscraper. The fuel requirements drop dramatically. The engineering becomes simpler. The cost plummets. This asymmetry between Earth and the moon is the foundation of everything that follows, because it means that anything you can build on the moon, anything you can manufacture there, Anything you can mine or extract or process on the lunar surface is vastly cheaper to launch into space than the same thing launched from Earth. A kilogram of material launched from the moon's surface into lunar orbit costs a fraction of what it costs to launch that same kilogram from Earth's surface into Earth orbit. This single fact changes the entire economics of space exploration. Now let's talk about something even more elegant. The space between Earth and the moon isn't just empty void. It contains invisible points of gravitational balance that are among the most valuable locations in the entire solar system. These are called Lagrange points, named after the Italian-French mathematician Joseph-Louis Lagrange, who first calculated their positions in 1772. Lagrange points are positions in space where the gravitational pull of two large bodies, in this case Earth and the Moon, and the centrifugal force of orbiting combine to create spots of relative gravitational equilibrium. There are 5 of them in the Earth-Moon system, labeled L1 through L5. A spacecraft placed at one of these points can remain there with minimal fuel expenditure, essentially parking in space. L1 sits between Earth and the Moon, about 61,000 kilometers from the Moon's surface. A station at L1 would have a continuous line of sight to both Earth and the Moon, making it an ideal communications relay point and transfer station. Spacecraft traveling from Earth to the Moon could stop at L1, refuel, reconfigure, and continue their journey. L2 sits behind the Moon, on the side facing away from Earth. This point is fascinating for a completely different reason. We'll get into this more later, but for now, understand that L2 is permanently shielded from Earth's radio emissions by the entire bulk of the Moon. It's one of the quietest spots in the inner solar system, which makes it incredibly valuable for certain kinds of astronomy. L4 and L5 are the stable points. They sit along the Moon's orbital path, 60 degrees ahead and 60 degrees behind the Moon, forming equilateral triangles with Earth and Moon at the other 2 corners. Objects placed at L4 or L5 tend to stay there. They naturally resist being pushed away. These points are sometimes called gravity traps because small objects accumulate there over time. In fact, astronomers have found clouds of dust at the Earth-Moon L4 and L5 points, trapped there by gravity. These Lagrange points transform the Earth-Moon system from 2 isolated bodies into a network of gravitationally favorable positions connected by low-energy transfer orbits. You can move between these points using remarkably little fuel, following paths that let gravity do most of the work. These paths are sometimes called the interplanetary transport network, and they're not science fiction. They're real orbital mechanics that mission planners use today. These low-energy pathways deserve a closer look because they're one of the most beautiful discoveries in modern orbital mechanics. Imagine space not as an empty void, but as a landscape shaped by gravity. Every massive body, the Earth, the Moon, the Sun, creates a kind of gravitational terrain around it. Hills and valleys and ridges of potential energy. The Lagrange points sit at the saddle points of this terrain, like mountain passes between gravitational valleys. And just as water flows naturally through mountain passes, spacecraft can drift along pathways that connect these saddle points, riding the contours of the gravitational landscape with almost no fuel. These pathways form tubes of possibility winding through space. A spacecraft that enters one of these tubes near a Lagrange point gets gently guided along a trajectory that can carry it enormous distances for almost zero energy expenditure. The catch is time. These low-energy transfers are slow. They can take months where a conventional high-thrust trajectory would take days. But for cargo, for fuel shipments, for robotic supply missions where speed doesn't matter, but fuel efficiency is everything, they're transformative. The mathematical foundations of these pathways were developed in the 1980s and 90s by mathematicians and physicists, including Edward Bell Bruno and others working at NASA's Jet Propulsion Laboratory. Bell Bruno showed that by carefully exploiting the gravitational interactions between the Sun, the Earth, and the Moon, spacecraft could reach the Moon using dramatically less fuel than conventional direct transfers. His work was considered theoretical until it was put to the test in a real mission. In 1990, Japan's Hayden spacecraft was in trouble. It had used most of its fuel and didn't have enough left for a conventional lunar orbit insertion. Using Bell Bruno's calculations, mission controllers sent Hayden on a long, looping trajectory that swung it out toward the Sun-Earth Lagrange points, and then let the combined gravity of the Sun, Earth, and Moon gently guide it back toward the Moon. It worked. Hayden reached lunar orbit using a fraction of the fuel a direct transfer would have required. It was the first spacecraft in history to demonstrate a low-energy ballistic capture at the Moon. Since then, low-energy transfers have been used by several missions. The European Space Agency's SMART 1 mission used a combination of ion propulsion and gravitational pathways to reach the Moon in 2003. NASA's GRAIL mission, which mapped the Moon's gravitational field, also used a low-energy transfer to reach lunar orbit. These missions proved that the gravitational architecture of the Earth-Moon system isn't just a curiosity, it's a usable transportation network. A network that already exists, built by physics, waiting for us to use it at scale. The practical implications are staggering. Imagine a future where fuel depots sit at L1, supplied by propellant manufactured on the Moon's surface. Spacecraft leaving Earth would only need to carry enough fuel to reach L1. There, they'd top off their tanks with fuel made from lunar resources and continue on to Mars, the asteroids, or beyond. The brutal cost of launching all that fuel from Earth's surface, fighting through our deep gravity well, would be eliminated. The Moon's shallow gravity well would supply the fuel instead. This isn't theoretical. The physics works. The orbits exist. The Lagrange points are real, measurable, and have been used by actual spacecraft. The James Webb Space Telescope, for example, orbits the Sun-Earth L2 point, about 1.5 million kilometers from Earth. NASA's Artemis mission has used the Earth-Moon Lagrange points for lunar orbital studies. These are proven concepts, not hopes. Now let's think about what makes the Moon uniquely suited for this role compared to any other body in the solar system. Why not Mars? Why not an asteroid? Why not one of Jupiter's moons? The answer comes down to a combination of 4 factors that no other body matches: proximity, gravity, resources, and position. Proximity. The Moon is 3 days away. Mars is 7 to 9 months away. If something goes wrong on a lunar mission, you can abort and come home. On Mars, you're stuck for at least 2 years, because you have to wait for the planets to align before you can make the return trip. The moon allows for rapid iteration. You can send missions frequently, test technologies, fix problems, and try again. Mars doesn't offer that luxury. Gravity. The moon's 1/6 gravity is low enough to make launches cheap, but high enough to keep things on the surface. On an asteroid, the gravity is so weak that walking would launch you into space. Equipment and habitats would need to be anchored. Dust kicked up by activity would float away. The moon's gravity is a sweet spot. It's light enough to be advantageous for launches, but heavy enough to work with practically. Resources. And this is something we'll come back to, because it changes everything. The moon has water ice locked in permanently shadowed craters near its poles. It has oxygen bound in its surface minerals. It has metals, silicon, and other materials that can be extracted and processed. You can make rocket fuel on the moon. You can make building materials. You can extract breathable oxygen. No asteroid offers this combination so close to Earth. Position. The moon's orbit around Earth places it at the edge of our gravity well, right at the point where deep space missions begin. It's not a detour. It's a natural first stop. The orbital mechanics of leaving Earth's neighborhood actually favor routes that pass near the moon. Many interplanetary trajectories use the moon's gravity to gain a speed boost, a technique called a gravity assist or gravitational slingshot. Gravity assists deserve a moment of explanation because they're one of the most elegant tricks in orbital mechanics. When a spacecraft passes close to a massive body like the moon or a planet, the body's gravity bends the spacecraft's path and can add or subtract speed relative to the sun. It's like a ball bouncing off a moving wall. If the wall is moving toward the ball bounces off faster. The moon is moving in its orbit at about 1 kilometer per second. A spacecraft passing close to the moon in the right direction can steal a little of that orbital energy, gaining speed without burning any fuel. NASA has used gravity assists extensively. The Voyager missions used Jupiter's gravity to reach Saturn and beyond. The Cassini spacecraft used Venus, Earth, and Jupiter to reach Saturn. These aren't tricks or shortcuts. They're fundamental physics. The energy comes from the body's orbital motion, and while the body technically slows down, the effect is so tiny it's completely unmeasurable. The moon loses an incomprehensibly small fraction of its orbital energy, and the spacecraft gains enough to reach another planet. The Earth-Moon system is particularly good at this because it's a two-body system that spacecraft can interact with repeatedly. A spacecraft in a high Earth orbit can make multiple passes near the moon, gaining energy each time, gradually building up to the velocities needed for interplanetary travel. This technique is called a multi-lunar gravity assist, and it could reduce the fuel needed for missions to Mars and beyond by a significant margin. Let me bring this all together because the picture that emerges is remarkable. Earth is surrounded by a deep gravity well. Getting out of this well is the hardest and most expensive part of any space mission. Once you're in orbit, you've already spent most of your energy. The moon sits at the edge of this well, close enough to reach quickly, with a gravity well of its own that's shallow enough to make launches almost trivially easy compared to Earth. Between the Earth and the moon are Lagrange points, gravitationally stable locations where fuel depots and stations could be placed. And the moon itself has the resources to produce fuel, oxygen, and building materials on site. what you end up with is not a single destination but a system. An integrated transportation network that uses the natural architecture of gravity to make deep space travel possible. Earth provides the people, the technology, the command and control. The moon provides the fuel, the materials, the launching platform. The Lagrange points provide the transfer stations and staging areas. And the whole system works because of physics, because of the specific arrangement of masses and distances and orbital mechanics that happens to exist in our corner of the solar system. This isn't luck, exactly, but it is fortunate. If the moon were much farther away, it would be too costly to develop as a waypoint. If it were much closer, tidal forces would create problems and its gravity well would be less useful. If it were much smaller, it wouldn't have the resources we need. If it were much larger, its gravity well would be deeper, making launches expensive. The moon we have is almost absurdly the right size, at the right distance, with the right gravity, in the right position to serve as the gateway to the rest of the solar system. Some people look at the moon and see a dead, barren rock, a place we've already been, a relic of the 1960s space race that doesn't need to be revisited. But that view misunderstands what the moon actually is in physical terms. It's not a trophy. It's not a monument to past achievement. It's a tool, the most useful tool humanity has for expanding beyond this planet. Every serious plan for sustained deep space exploration, whether to Mars, to the asteroid belt, or beyond, benefits enormously from the moon, not as a detour, but as a foundation. The Apollo missions proved we could get to the moon and back. That was extraordinary for its time, but Apollo was a sprint. Astronauts spent at most 3 days on the surface. They explored a few kilometers around their landing sites. They brought back a few hundred kilograms of rocks. And then we left and didn't go back for more than 50 years. What's happening now is fundamentally different. We're not going back to plant flags and leave footprints. We're going back to build the infrastructure that makes everything else possible. Fuel depots, landing pads, habitats, communication relays, power stations. The moon is going to become the first permanent human outpost beyond Earth, not because it's glamorous, but because the physics demands it. There's a beautiful irony here. The moon seems so close, so familiar. You can look up on a clear night and see it with your naked eye. You can see its craters with a cheap pair of binoculars. It's been hanging there in our sky for as long as humans have existed, so constant and familiar that we barely notice it anymore. But this familiar companion, this object we take completely for granted, turns out to be the single most important stepping stone for everything humanity wants to do in space. Every kilogram of fuel that doesn't have to be launched from Earth's surface is a kilogram of payload that can be science equipment, life support supplies, or construction materials. Every mission that can refuel at the moon, instead of carrying all its propellant from Earth, can go farther, carry more, and accomplish more. Every technology tested on the moon under real space conditions, 3 days from home, is a technology that doesn't have to be tested for the first time on Mars, 9 months from help. The gravity ladder we need to climb to reach the rest of the solar system doesn't start at Earth's surface. It starts at the moon. And the moon, sitting quietly in our sky, has been waiting there all along, 4.5 billion years, patiently orbiting, silently offering the exact set of physical conditions that a spacefaring civilization needs. We just had to learn enough physics to understand why. But the moon isn't just a gravitational stepping stone. Its surface holds secrets that go far beyond orbital mechanics. Secrets that are billions of years old. Secrets that Earth itself has long since destroyed. And to understand why those secrets matter, we need to talk about what Earth has been doing to its own history for the past 4.5 billion years. Now let's talk about something that most people never consider when they think about the moon. Something that transforms it from a dead grey rock into one of the most scientifically precious objects in the entire solar system. The moon is an archive, a library, a record keeper that has been silently documenting the history of our solar system for 4.5 billion years. And the reason this matters so much is that the only other place we'd want to look for these records, our own planet Earth, destroyed them all a long time ago. To understand why the moon's surface is so valuable, you first have to understand what Earth has been doing to its own surface since the planet formed. And the answer is erasing it. Constantly, relentlessly, thoroughly erasing it. Earth is a geologically hyperactive planet. Beneath the thin crust you're standing on right now, the interior is churning. The mantle, a layer of hot rock, roughly 2,900 kilometers thick, flows in slow convection currents, driven by heat from the core. This convection drives plate tectonics, the process by which Earth's crust is broken into massive plates that slide, collide, and dive beneath one another over millions of years. When two plates collide, one could be forced beneath the other in a process called subduction. The descending plate sinks into the mantle, where it's heated and eventually recycled back into molten rock. The surface material, everything that was on that plate, all the rocks, all the minerals, all the geological record of whatever happened there, gets melted and destroyed. Meanwhile, new crust forms at mid-ocean ridges where magma pushes up from below, solidifying into fresh rock. The entire ocean floor is recycled roughly every 200 million years. There is no ocean floor on Earth older than about 200 million years. It's all been swallowed and replaced, but plate tectonics isn't the only force erasing Earth's records. There's also erosion. Wind, water, and ice have been grinding down Earth's surface features for billions of years. Mountains rise and are worn down. River valleys carve through rock. Glaciers scrape continents flat. Coastlines shift. Deserts bury landscapes under sand. Rain, the simple everyday rain that you barely think about, is a slow-motion demolition crew that dissolves minerals and carries them to the sea over millions of years. Then, there's the atmosphere. Earth's atmosphere is chemically active. Oxygen, which makes up about 21% of our air, is a highly reactive element. It corrodes metals, weathers rocks, and chemically transforms minerals. Iron rusts, limestone dissolves in slightly acidic rain. Silicate rocks slowly break down into clays. The atmosphere is a chemical engine that steadily degrades everything exposed to it. And then there's life. Life has been reshaping Earth's surface for nearly 4 billion years. Microbes break down rocks. Plants send roots into crevices, splitting stone apart. Organisms build reefs, create soil, alter the chemistry of oceans and atmosphere. The Great Oxidation Event, roughly 2.4 billion years ago, fundamentally transformed Earth's atmosphere when photosynthetic organisms flooded it with oxygen. That single biological event changed the chemistry of the entire planet's surface. The result of all these processes is that Earth has almost no surface record of its first billion years of existence. Geologists call this period the Hadean era, from the Greek word for underworld. It was a time when Earth was still cooling from its formation, when the surface was likely covered in magma oceans, when the planet was being bombarded by asteroids and comets left over from the solar system's formation. This was the most dramatic and formative period in Earth's history, and we know almost nothing about it from direct evidence because Earth has recycled, eroded, weathered, and biologically processed virtually every trace of that era out of existence. The oldest rocks on Earth's surface are about 4 billion years old. They're found in small outcrops in places like northern Canada and Western Australia, but they're rare, heavily metamorphosed, and they represent only tiny fragments of what once existed. Trying to reconstruct Earth's first billion years from these scraps is like trying to reconstruct an entire library from a few charred pages. Now consider the Moon. The Moon has no plate tectonics. Its interior cooled long ago. There are no convection currents driving crustal recycling, no plates sliding over one another, no subduction zones swallowing ancient surfaces. The crust that formed billions of years ago is still there, right where it formed, undisturbed. The Moon has no atmosphere, no wind, no rain, no chemical weathering. A footprint left in the lunar dust by an Apollo astronaut will remain there, perfectly preserved for millions of years. The only things that disturb the surface are micrometeorite impacts, tiny particles hitting the surface at high speeds and very slowly churning the top few centimeters of dust over millions of years. This process, called gardening, is incredibly slow compared to anything that happens on Earth. Surfaces that are billions of years old look essentially the same as they did when they formed. The Moon has no liquid water. Water is one of the most powerful erosive forces in nature. It carves canyons, dissolves minerals, transports sediment, and chemically alters rocks. The Moon has none of this. The surface is bone dry in most places, preserved in a state that would be impossible on any world with oceans or rivers. The Moon has no life, no organisms breaking down rocks, no roots cracking stone, no biological chemistry altering the surface. The lunar surface is as sterile as it was the day the Moon formed. Nothing has grown there. Nothing has metabolized there. Nothing has changed the chemistry through biological processes. What this means is extraordinary. The Moon's surface is a geological time capsule that stretches back to the very formation of the solar system. Events that happened 4 billion years ago are recorded on the Moon's surface in a way that's readable, interpretable, and accessible. You just have to go there and look. And the most dramatic events recorded there are the impacts. The Moon's surface is covered in craters, thousands upon thousands of them, ranging from microscopic pits to enormous basins hundreds of kilometers across. Each one is a record of a collision, an asteroid or comet that struck the lunar surface at tremendous speed. And because the Moon has no processes that erase craters, they accumulate. Layer upon layer, older craters overlapped by newer ones, creating a readable chronology of bombardment that stretches across billions of years. This cratering record is one of the most important datasets in planetary science. By studying the density and distribution of craters on different lunar surfaces, and by dating rock samples from those surfaces, scientists have been able to construct a timeline of impacts in the inner solar system. This timeline revealed something astonishing. About 3.9 billion years ago, the inner solar system experienced a dramatic increase in impact rates. A period of intensified bombardment that geologists call the Late Heavy Bombardment, or sometimes the Lunar Cataclysm. During this period, which may have lasted a few 100 million years, enormous numbers of asteroids and comets rained down on the Moon, Earth, Mars, Mercury, and Venus. The largest impacts create the vast dark plains on the Moon that we can see with the naked eye. The Maria. These are enormous basins that were excavated by asteroid impacts and later flooded with basaltic lava from the Moon's interior. The Late Heavy Bombardment fundamentally shaped the inner solar system. On the Moon, it created the landscape we see today. On Earth, it may have sterilized the planet's surface repeatedly, boiling the oceans and melting the crust. Some scientists believe that the Late Heavy Bombardment may also have delivered water and organic molecules to Earth, potentially seeding the conditions for life. Others think life may have emerged during brief calm periods between major impacts, only to be wiped out and forced to start over. The timing is still debated, but the evidence from the Moon is what made us aware this event happened at all. We only know about the Late Heavy Bombardment because of the Moon. Earth has no record of it. The impacts that struck Earth during this period have been completely erased by billions of years of geological activity. Mars retains some cratering record, but its surface has also been modified by volcanic activity, water erosion, and atmospheric processes. The Moon alone preserves a clear, readable record of this cataclysmic period. But craters aren't the only records the Moon preserves. The lunar soil itself, the regolith, is a treasure trove of information that goes far beyond impact history. The lunar regolith is a layer of broken rock, dust, and glass fragments that covers the Moon's entire surface. It ranges from about 2 meters deep in younger areas to perhaps 20 meters deep in older highland regions. This material has been created over billions of years by the constant bombardment of micrometeorites, which shatter and pulverize the surface rock into ever finer particles. Here's what makes the regolith scientifically extraordinary. The Moon has no magnetic field to speak of and no atmosphere. This means the lunar surface is directly exposed to the solar wind, the constant stream of charged particles flowing outward from the Sun. These particles, mostly hydrogen and helium ions, but also heavier elements, strike the lunar surface and become embedded in the top layers of the regolith grains. The regolith is essentially a recording medium for the Sun's output. By analyzing the composition and abundance of solar wind particles embedded in different layers of regolith, scientists can reconstruct the history of the Sun's activity over billions of years. How has the Sun's luminosity changed? How has the composition of the solar wind varied? Has the Sun experienced periods of unusually high or low activity? The answers to these questions are written in the lunar soil, waiting to be read. This is information we cannot get from Earth. Earth's magnetic field and atmosphere shield us from the solar wind. We have no direct record of solar activity beyond a few thousand years of ice core data and a few hundred years of direct observation. The moon has been recording the sun's behavior since the solar system was young. The regolith also contains a record of galactic cosmic rays, high-energy particles from outside the solar system. These particles come from supernovae, neutron star collisions, and other violent astrophysical events. When they strike the lunar surface, they interact with the regolith in measurable ways. By studying these interactions, scientists can learn about the cosmic ray environment in our part of the galaxy over billions of years. Has the cosmic ray flux changed? Have there been periods of unusually high radiation, perhaps caused by a nearby supernova? The moon's surface holds these answers, and there's another kind of record preserved in the regolith that's almost poetic in its implications. Meteorite impacts on Earth blast pieces of our planet's surface into space. Some of these fragments, after drifting through space, eventually land on the moon. Earth meteorites on the lunar surface could contain minerals, fossils, or chemical signatures from Earth's earliest history. From periods so ancient that Earth itself has destroyed all traces of them. There could be pieces of the Hadean Earth sitting on the moon right now. Fragments of our planet's surface from 4 billion years ago, preserved in the lunar vacuum while Earth erased every trace of that era from its own surface. In fact, scientists believe they may have already found evidence of this. A rock sample brought back by the Apollo 14 mission, catalogued as Sample 14321, contains a fragment that appears to be Earth rock. Analysis suggests it was formed under conditions consistent with Earth's interior, not the moon's. If confirmed, this fragment is about 4 billion years old, making it one of the oldest pieces of Earth ever found. And it was found on the moon. Now, let's talk about one of the most scientifically valuable locations in the entire solar system, the South Pole Aitken Basin. This is a massive impact crater on the moon's far side, near the South Pole. It stretches roughly 2,500 kilometers across and is about 8 kilometers deep, making it one of the largest and oldest impact structures in the entire solar system. The South Pole Aitken Basin was created by an enormous asteroid impact, roughly 4.3 billion years ago, early in the moon's history. The impact was so violent that it may have excavated material from deep within the moon's mantle, bringing material to the surface that normally lies hundreds of kilometers below the crust. This is extraordinary because it gives us access to the moon's deep interior without having to drill. The composition of the mantle tells us about the moon's formation, its thermal history, and the conditions that existed in the early solar system. The basin is also old enough that it predates the late heavy bombardment. Studying the craters that overlay it can help scientists calibrate the chronology of impacts across the entire solar system. Getting precise age measurements from the South Pole Aitken Basin is one of the highest priorities for lunar science. And it's one of the key reasons missions are targeting the lunar South Pole region. All of this brings us to a deeper question. How did the moon form in the first place? Because the answer to that question is directly connected to the history of Earth and to the formation of the entire inner solar system. The leading theory is called the giant impact hypothesis. According to this model, about 4.5 billion years ago, a Mars-sized body, sometimes called Theia, collided with the young Earth. The impact was catastrophic. It was not a glancing blow or a gentle merger. It was a collision of staggering violence. The energy released was enough to partially melt both bodies. Enormous amounts of debris were blasted into orbit around the Earth, and this debris gradually coalesced to form the Moon. This hypothesis explains several key observations. The Moon's composition is very similar to Earth's mantle, which makes sense if it formed from material ejected from Earth's outer layers. The Moon has a much smaller iron core than expected for a body its size, which makes sense if the iron from Theia's core merged with Earth's core during the impact, rather than being launched into orbit. The Moon's orbit and angular momentum are consistent with a giant impact scenario. But there are still unresolved questions. The isotopic composition of lunar samples is almost identical to Earth's, which is puzzling because Theia should have had a different isotopic signature. If the Moon formed partly from Theia's material, we'd expect to see some differences. The fact that we don't see significant differences suggests either that Theia had a very similar composition to Earth, which would be an unlikely coincidence, or that the impact was so energetic that it completely mixed the materials from both bodies, erasing any compositional differences. These questions can only be answered with more samples from more locations on the Moon. The Apollo mission sampled only 6 sites, all on the near side, all relatively close to the lunar equator. That's like trying to understand Earth's geology by sampling 6 spots in the Sahara Desert. We need samples from the far side, from the poles, from the interiors of ancient basins, and from the highlands. Each new sample has the potential to rewrite what we know about the Moon's origin, and, by extension, about the early Earth. There's something else the Moon can tell us that might be the most surprising of all. The Moon once had a magnetic field. Today, the Moon has no global magnetic field. Its core is too cool and too small to generate one. If you took a compass to the lunar surface right now, the needle would just drift aimlessly. But studies of lunar rocks brought back by the Apollo missions revealed something unexpected. Some of those rocks had been magnetized. They recorded the presence of a magnetic field at the time they formed, much the way a compass needle aligns with Earth's field. This means that billions of years ago, the Moon had an active magnetic dynamo in its core, generating a field strong enough to magnetize surface rocks. And not just a weak field. When scientists measured the remnant magnetism in Apollo samples, they found evidence of a field that was astonishingly strong. Some studies suggest the lunar magnetic field around 3.5 to 4 billion years ago may have reached intensities of up to 100 microtesla. To put that in perspective, Earth's magnetic field today is typically between 25 and 65 microtesla at the surface. The ancient Moon may have had a magnetic field as strong as Earth's current one. From a body that small, with a core that tiny, that's remarkable. And frankly, it's a puzzle. On Earth, the magnetic field is generated by what's called a dynamo, convection currents of molten iron churning in the outer core, driven by heat from the inner core. The rotation of the planet organizes these currents into a coherent magnetic field that extends far into space. But the moon's core is small, estimated at roughly 300 to 400 kilometers in radius, and it should have cooled relatively quickly. A conventional core dynamo should have died out early in the moon's history. Yet the rock samples suggest the field persisted far longer than it should have. Scientists have proposed several explanations. One is that the early moon's core was kept stirred not just by internal heat, but by tidal forces from Earth. When the moon was much closer to Earth billions of years ago, tidal interactions may have been strong enough to mechanically stir the liquid core, driving a dynamo even without sufficient internal heat. Another proposal suggests that large impacts could have temporarily destabilized the moon's mantle, creating short-lived bursts of core convection and magnetic field generation. What makes this even more intriguing is that the magnetic field appears to have declined in two distinct phases. The strong field persisted until roughly 3.5 billion years ago, then weakened significantly. But a weaker field seems to have lingered for much longer, possibly until about 1 billion years ago, before finally dying out completely. Why two phases? What changed inside the moon at those moments? We don't fully know. Answering these questions requires more samples from more locations, particularly from terrains of different ages, so scientists can trace the magnetic history with greater precision, and the implications extend far beyond the moon. Mars also had a magnetic field once. Mars also lost it. And when Mars lost its magnetic field, the consequences were devastating. Without magnetic protection, the solar wind stripped away Mars's atmosphere over hundreds of millions of years, transforming it from a warm, wet world with liquid water on its surface into the cold, desiccated desert we see today. The loss of Mars's magnetic field may be the single most important event in that planet's history, the moment it went from potentially habitable to essentially dead. If we can understand why the moon's magnetic field died, the mechanisms that sustained it, and the processes that killed it, we might better understand why Mars's field died. And that, in turn, helps us understand what conditions are necessary for a planet to maintain the kind of magnetic shield that protects atmospheres and, potentially, life. The answer might be written in lunar rocks that haven't been collected yet, from regions that haven't been explored, waiting for missions that are being planned right now. Every time we study the moon, we're not just learning about the moon. We're learning about the processes that shaped every rocky world in the inner solar system. The moon is a reference point, a calibration standard for all of planetary science. Let me give you a specific example of how powerful this calibration can be. Before the Apollo missions, scientists had no reliable way to determine the age of surfaces on other planets. They could count craters and guess, but without absolute age measurements, their estimates were just that, guesses. The Apollo astronauts brought back 382 kilograms of lunar rocks from 6 different landing sites. Scientists used radiometric dating to determine the precise ages of those rocks and the surfaces they came from. This allowed them to calibrate the relationship between crater density and surface age. More craters mean an older surface, but now they knew exactly how many craters corresponded to how many billions of years. This calibration, called the lunar chronology, was then applied to every other rocky body in the solar system. When scientists look at Mars and count the craters in a particular region, They use the lunar chronology to estimate that region's age. The same is true for Mercury, for asteroids, for the moons of Jupiter and Saturn. Every age estimate for every surface on every rocky body in the inner solar system is ultimately traceable back to those Apollo samples. The moon provided the yardstick by which we measure the age of everything else. But here's the problem. Those 6 Apollo landing sites sampled a limited range of ages and terrains. The calibration has gaps. There are age ranges where we have no samples, which means our estimates for surfaces of those ages on other planets are uncertain. Every new sample from a previously unsampled region of the moon tightens the calibration. Every new data point makes our understanding of the entire solar system's history more precise. This is one of the reasons scientists are so excited about returning to the moon. Not just for the moon's own sake, though that's compelling enough, but because every new lunar sample improves our understanding of Mars, Mercury, the asteroid belt, and beyond. The moon is the Rosetta Stone of planetary science. It's the key that unlocks the history of the entire inner solar system. Think about what the moon has preserved for us. A record of every major impact event for 4.5 billion years. A record of the sun's behavior over that same period, written in solar wind particles embedded in the soil. A record of cosmic ray activity from beyond the solar system. Possible fragments of ancient Earth. Pieces of our own planet's infancy that no longer exist on Earth. Evidence of the moon's own magnetic history. Clues to the giant impact that formed the Earth-Moon system. A chronological calibration standard that underpins our understanding of every rocky world. All of this is sitting there, right now, on a world we can reach in less than a week. A world we've visited before. A world we know how to get to. A world where the records are exposed on the surface, waiting to be collected by astronauts or robotic missions. Earth has a 4.5 billion year history, but it destroyed the evidence. The moon has the same history, and it kept every page. The geological record on the moon isn't just lunar history, it's our history. It's the history of our planet, our sun, our solar system, and the violent, chaotic processes that ultimately led to the conditions that allowed life to emerge on Earth. When astronauts return to the moon and dig into the regolith, when they crack open ancient rocks from the South Pole Aitken Basin, when they drill cores from the permanently shadowed craters at the poles, they won't just be doing lunar science. They'll be reading the oldest, most complete history book in the solar system, a book that only the moon could have preserved. And the moon has one more gift to offer science, one that has nothing to do with geology or history. The moon's physical environment, its vacuum, its silence, its exposure to the full harshness of space, makes it the most powerful scientific laboratory humanity could ask for. A laboratory for experiments that are literally impossible to perform anywhere else. And the reasons why start with something that sounds deceptively simple: empty space. The moon is a gravitational stepping stone. It's an ancient geological archive. But it's also something else. Something that might be the most surprising reason of all for going back. The moon is a laboratory. Not a laboratory in the way you might picture, with white walls and fluorescent lights and people in lab coats. It's something far more powerful than that. The moon is a natural laboratory with physical conditions that we cannot replicate on Earth. Conditions that make certain experiments not just easier but possible for the first time in the history of science. And the first of these conditions is the one that seems the most boring until you understand its implications: the vacuum. When we say the moon has no atmosphere, most people think of that simply as a hazard. No air to breathe, spacesuits required. But from a scientific and engineering perspective, the lunar vacuum is not a hazard. It's a treasure. The moon's surface exists in a vacuum comparable to the very best vacuum chambers we can create on Earth. But here's what matters. The best vacuum chambers on Earth are tiny, extraordinarily expensive, and require constant pumping to maintain. The moon offers that same quality of vacuum for free, across an area of 38 million square kilometers. No walls, no pumps, no power consumption, just empty space, stretching from horizon to horizon. On Earth, creating a vacuum is extraordinarily difficult and expensive. Every vacuum chamber has walls, and those walls constantly release gas molecules from their surfaces, a process called outgassing. No matter how powerful your pumps are, no matter how carefully you prepare your chamber, there are always residual gas molecules bouncing around inside. The best vacuum chambers on Earth, the ones used in advanced semiconductor fabrication and particle physics experiments, can achieve pressures comparable to the lunar surface, but they do it inside a container the size of a room, at enormous cost, with pumps running continuously. The moon does it across an entire world, for nothing. Why does this matter? Because many advanced manufacturing processes and scientific experiments require a vacuum. Growing certain types of crystals, manufacturing ultra-pure materials, depositing thin films of atoms onto surfaces, all of these processes are limited by the quality of the vacuum they're performed in. Stray gas molecules contaminate surfaces, introduce defects into crystal structures, and reduce the purity of manufactured materials. On the moon, you could perform these processes in the open, on the surface, without any chamber at all. The vacuum is already there, better than anything you could build. Materials science experiments that are limited by vacuum quality on Earth could be performed with far greater precision on the moon. Thin film deposition, which is critical for manufacturing solar cells, semiconductors, and optical coatings, could achieve purities that are simply unattainable in terrestrial laboratories. There's another aspect of the vacuum that matters for physics. Certain particle physics experiments require beams of particles to travel long distances without colliding with gas molecules. On Earth, this requires building enormously long vacuum tubes, which are expensive and technically challenging. The Large Hadron Collider at CERN, the world's largest particle accelerator, uses a vacuum tube 27 kilometers in circumference, pumped down to a pressure comparable to the lunar surface. But maintaining that vacuum across 27 kilometers of tube requires an enormous system of pumps running continuously. On the moon, you could build a particle accelerator where the beam travels in the open. No tube, no pumps. The vacuum is already there, stretching across the entire surface. A lunar particle accelerator could potentially be far larger and far cheaper than anything built on Earth, opening up new frontiers in particle physics. But the vacuum is just the beginning. Let's talk about what might be the moon's single most valuable scientific asset: its silence. Right now, as you listen to this, you are bathed in radio waves. They're everywhere. Radio stations, television broadcasts, cell phone signals, Wi-Fi routers, satellite transmissions, radar systems, microwave ovens, power lines, even the electrical activity of your own brain produces faint electromagnetic signals. Earth is drowning in radio noise. We've been broadcasting electromagnetic radiation into space since the early 20th century. And the cumulative effect is that the electromagnetic environment near Earth is incredibly noisy. This is a serious problem for radio astronomy. Radio telescopes on Earth have to deal with this constant background of human-made interference. Even telescopes built in remote locations, in deserts and mountains far from cities, still pick up radio noise from satellites overhead, from aircraft, from distant transmitters bouncing signals off the ionosphere. Astronomers have to use sophisticated filtering techniques to separate the signals they're looking for from the cacophony of human-made noise. And for some signals, the ones that are incredibly faint, the noise simply overwhelms them. They're lost, undetectable. No matter how sensitive your telescope is, if the noise is louder than the signal, you can't hear it. Now, consider the far side of the moon. The side that permanently faces away from Earth. Standing on the far side, the entire bulk of the moon, 3,474 kilometers of solid rock, sits between you and Earth. Every radio transmission, every television broadcast, every Wi-Fi signal, every electromagnetic emission from our planet is blocked completely. The far side of the moon is the most radio-quiet location in the entire inner solar system that's accessible to us. This isn't a minor advantage. It's transformative. There are observations that can only be made from a radio-quiet environment. Observations that could reshape our understanding of the universe. The most exciting of these involves what cosmologists call the cosmic dark ages. This is the period between about 380,000 years and roughly 200 million years after the Big Bang. During this time, the universe had cooled enough for atoms to form, but no stars had yet ignited. The universe was dark. No light sources existed anywhere. The only thing filling space was hydrogen gas, slowly cooling, slowly clumping together under gravity, preparing for the moment when the first stars would eventually burst into existence. This hydrogen gas emitted radio waves at a very specific frequency, 21 centimeters, corresponding to a natural transition in hydrogen atoms. But because the universe has been expanding for billions of years, those radio waves have been stretched. Their wavelength has been redshifted from 21 centimeters to wavelengths of several meters, corresponding to frequencies of about 1 to 50 megahertz. To understand why this matters so much, you need to appreciate what the cosmic dark ages actually look like. Imagine the entire universe with no light. None. No stars, no galaxies, no nebulae, no glowing gas clouds. Nothing but vast, formless expanses of hydrogen and helium gas, slowly cooling in the aftermath of the Big Bang. The cosmic microwave background, the oldest light in the universe, had already been released about 380,000 years after the Big Bang, when the universe cooled enough for the atoms to form. After that moment, the universe went dark. The gas was too cool to glow in visible light, and nothing else existed to illuminate it. This darkness lasted for roughly 200 million years. An immense span of cosmic time during which the only thing happening was gravity, slowly, patiently pulling matter together, building the density concentrations that would eventually collapse into the first stars. We currently know almost nothing about this period from direct observation. Our best picture of the early universe comes from the cosmic microwave background, which has been mapped in extraordinary detail by satellites like COBE, WMAP, and Planck. But the cosmic microwave background is a snapshot of a single moment, the instant when light first escaped the primordial plasma. It tells us what the universe looked like at 380,000 years old. After that, we have a gap. A vast observational gap stretching from 380,000 years to roughly 200 million years. When the first stars finally ignited and began producing light again. The cosmic dark ages sit inside that gap, completely unobserved, invisible, but not silent. That hydrogen gas was emitting 21 centimeter radiation the entire time, and the information encoded in that radiation is staggering. The cosmic microwave background, as powerful as it is, gives us essentially a two-dimensional map of the universe at one moment in time. The Dark Ages signal, by contrast, is three-dimensional. Because the radiation was emitted continuously over hundreds of millions of years, and because radiation from different epochs has been redshifted by different amounts, we can in principle reconstruct a full three-dimensional volume of the early universe, layer by layer, epoch by epoch. The amount of information contained in the Dark Ages signal dwarfs the cosmic microwave background by orders of magnitude. Some cosmologists have estimated that the Dark Ages signal contains roughly 100 trillion times more information than the cosmic microwave background. This isn't just about mapping where matter was. The patterns in the Dark Ages signal could reveal the nature of dark matter. They could constrain the mass of neutrinos. They could test whether the fundamental constants of physics have changed over cosmic time. They could reveal whether exotic processes occurred in the early universe that our current theories don't predict. It's arguably the single richest untapped dataset in all of observational science. And it's been flowing through the universe for over 13 billion years, waiting for someone to build a telescope quiet enough to hear it. The technical challenges are formidable, but work has already begun. China's Chang'e 4 mission, which landed on the far side of the moon in 2019, carried a low-frequency radio spectrometer designed to take preliminary measurements in this frequency range. To relay communications from the far side back to Earth, China positioned a satellite called Queqiao at the Earth-Moon L2 Lagrange point. Queqiao also carries a radio astronomy instrument. These are Pathfinder missions, early steps towards the much larger observatories that would be needed to detect the full Dark Ages signal. NASA, the European Space Agency, and several other groups are developing concepts for far-side radio arrays. Networks of simple antennas spread across the lunar surface that could work together as a single, enormous telescope. Here's the problem. On Earth, these frequencies are used by FM radio stations, television broadcasts, and various communication systems. The signals from the cosmic Dark Ages, already unimaginably faint after traveling for more than 13 billion years, are completely buried under human-made radio noise at these frequencies. No telescope on Earth can detect them. No telescope in Earth orbit can detect them, either because Earth's radio emissions extend far into space, but a radio telescope on the far side of the moon, shielded from Earth's noise by thousands of kilometers of rock, could potentially detect these signals. And what those signals would tell us is extraordinary. They would reveal how matter was distributed in the universe before the first stars formed. They would show us the seeds of the cosmic structures that eventually became galaxies and galaxy clusters. They would provide a map of the universe at an age we've never been able to observe, filling in a gap in our cosmic history that currently represents one of the biggest unknowns in all of cosmology. Some scientists believe that observations of the Dark Ages could also reveal information about dark matter and dark energy, the mysterious components that make up roughly 95% of the universe's total energy content. The way hydrogen was distributed during the Dark Ages was influenced by dark matter, and any anomalies in the expected patterns could provide clues about what dark matter actually is. The far side of the moon is literally the only place in our reach where these observations can be made. Not the best place, not the most convenient place, the only place. There is no alternative. If we want to study the cosmic dark ages through radio astronomy, we have to go to the moon. NASA has already begun exploring this idea. A concept called the Lunar Crater Radio Telescope proposes building a radio telescope inside a crater on the far side, using the natural bowl shape of the crater as a reflector dish. The telescope would operate at frequencies below 50 MHz, precisely the range needed to detect signals from the Dark Ages. It will be deployed by robots before any human ever set foot there. But servicing it, upgrading it, and expanding it would benefit enormously from having human presence on the moon. Now let's shift from the electromagnetic environment to something biological. Something that affects every human being who will ever travel beyond Earth. We know what zero gravity does to the human body. We've studied it extensively on the International Space Station, where astronauts live and work in microgravity for months at a time. The results are concerning. In zero gravity, muscles atrophy. Bones lose density at a rate of about 1 to 2% per month. The heart weakens because it doesn't have to work as hard to pump blood. Fluid shifts toward the head, increasing pressure in the skull, which can cause vision problems. The immune system changes. The spine elongates, which sounds interesting until you realize it can cause herniated discs and back pain. After 6 months on the International Space Station, astronauts need significant time to readapt to Earth gravity. Some can barely stand when they first return. We also know what full gravity does to the human body. That's just normal life on Earth. Our bodies evolved over millions of years to function at 1G, and they work perfectly well under these conditions. But here's the enormous gap in our knowledge. We know 0G is bad. We know 1G is fine. We know absolutely nothing about what happens in between. We have no data on what partial gravity does to the human body over extended periods. Is 1/6G enough to prevent bone loss? Does 1/3 G, the gravity on Mars, keep muscles from atrophying? At what point on the spectrum between 0 and 1G do the negative health effects begin to appear? Is there a threshold below which partial gravity is almost as bad as no gravity? Or does even a small amount of gravity provide significant protection? These questions are not academic. They are critical for the future of human space exploration. Mars has about 1/3 of Earth's surface gravity. If 1/3 g is not enough to maintain human health over months or years, then long-term human habitation of Mars may not be possible without artificial gravity or extensive medical intervention. If it turns out that 1/6 g is sufficient to prevent the worst effects of microgravity, then the Moon and Mars are both viable for long-term habitation. But we don't know. We have never performed long-duration studies of human physiology in partial gravity. Not once. Not even once. The International Space Station can't help us here because it's in free fall, which produces microgravity. There are centrifuge concepts that could simulate partial gravity on a space station, but they have significant limitations. The radius of a centrifuge affects how the artificial gravity is distributed across the body, and small centrifuges create problematic gradients where your head is at a noticeably different gravity than your feet. To avoid these issues, you'd need an extremely large centrifuge, which would be prohibitively expensive to launch and assemble in orbit. The Moon offers something no space station can provide: a natural 1/6 g environment across an entire world. Astronauts living on the Moon for months or years would provide the first ever long-duration data on human physiology in partial gravity. Scientists could monitor bone density, muscle mass, cardiovascular health, immune function, vision, and dozens of other physiological parameters. They could compare results to microgravity data from the ISS and normal gravity data from Earth. For the first time, we'd start to fill in the vast blank space between 0 and 1g on the graph of human health versus gravity. This data is essential before we send humans to Mars. A Mars mission with current technology means a crew spends roughly 6 to 9 months in zero gravity during transit, then lands on a planet with 1/3 g, then spends months or years on the surface, then endures another 6 to 9 months of zero gravity on the return trip. If 1/3 g isn't enough to maintain health, the crew could arrive on Mars too debilitated to function. They'd be weak, dizzy, prone to fractures, with impaired vision and compromised immune systems, stranded on a world 9 months from the nearest hospital. Understanding partial gravity physiology before attempting this journey isn't just prudent. It's a moral obligation to the people we'd be sending. The Moon is the only place in the solar system where we can study this safely. It's close enough that astronauts in medical trouble can return to Earth within days. It has enough gravity to provide meaningful partial gravity data, and it can host the kind of long-duration stays needed to observe how the human body adapts over months and years. Now, let's talk about radiation. This is another area where the Moon serves as an irreplaceable research platform. Earth's surface is protected from most space radiation by two shields: the atmosphere and the magnetic field. The atmosphere absorbs and scatters incoming particles. The magnetosphere, generated by molten iron churning in Earth's core, deflects charged particles from the solar wind and reduces the flux of galactic cosmic rays. These twin shields make Earth's surface one of the most radiation-protected environments in the solar system. The Moon has neither of these shields, no atmosphere, no global magnetic field. The lunar surface is exposed to the full radiation environment of deep space. Solar wind particles strike the surface directly. Solar flares can send intense bursts of high-energy particles washing over the Moon with no warning and no protection. galactic cosmic rays, high-energy particles from exploding stars, and other violent astrophysical events far beyond our solar system rain down continuously. This sounds like a hazard, and it is a hazard for human health. But it's also an invaluable research opportunity. Understanding the radiation environment in deep space is absolutely critical for long-duration missions to Mars and beyond. Astronauts on the International Space Station are partially protected by Earth's magnetosphere, which deflects many of the most dangerous particles. But astronauts traveling to Mars will spend months outside the magnetosphere, exposed to the full deep space radiation environment. We have models of this radiation environment, but models are only as good as the data they're based on. The Moon offers a platform for directly measuring and studying deep space radiation in a way that's impossible from Earth and limited from low Earth orbit. Instruments on the lunar surface can measure the full spectrum of incoming particles, their energies, their frequencies, their temporal patterns. These measurements over months and years would dramatically improve our radiation models and help us design better shielding for future spacecraft and habitats. The Moon also allows us to test radiation shielding materials and designs under real conditions. You can expose different materials to the actual deep space radiation environment and measure how well they attenuate different types of particles. You can bury habitats under regolith and measure how the radiation levels change with depth. You can test active shielding concepts, electromagnetic fields designed to deflect charged particles, in an environment where they're actually needed, rather than in a simulation. Every result feeds directly into the design of spacecraft and habitats for Mars and beyond. Let's move to another kind of science the Moon enables. Seismology. The Apollo missions placed seismometers on the lunar surface at several landing sites. These instruments operate from 1969 to 1977, and the data they returned was strange. When the Apollo 12 astronauts deliberately crashed their spent lunar module ascent stage into the Moon's surface to create an artificial moonquake, the seismometers recorded something unexpected. The Moon rang like a bell. The vibrations continued for over an hour, far longer than a similar event would produce on Earth. This prolonged reverberation told scientists that the Moon's interior is remarkably different from Earth's. The lunar crust is dry, rigid, and heavily fractured from billions of years of impacts. There's no water to dampen vibrations. The fractures scatter seismic waves in complex patterns, causing them to bounce around for extended periods. The data suggested that the Moon has a small iron core, a partially molten layer around it, and a thick, rigid mantle. But the Apollo seismic network was limited. Only 4 stations operated simultaneously at their peak, and they were all on the near side, clustered relatively close together. To truly map the Moon's interior, you need a global network of seismometers, including stations on the far side and near the poles. With a modern seismic network, scientists could determine the precise size and composition of the Moon's core. They could map the structure of the mantle in detail. They could identify any remaining pockets of partial melt. They could measure the thickness of the crust at many different locations. This matters beyond just understanding the Moon. Seismology is how we understand the interiors of all rocky bodies. The techniques and models developed for lunar seismology directly inform our understanding of Mars, Mercury, and even exoplanets. A detailed seismic map of the moon would provide a reference model for a small, differentiated rocky body, something we could compare against data from other worlds. NASA's InSight mission placed a seismometer on Mars in 2018 and detected Mars quakes, revealing details about the Martian interior. But a single station on Mars has limitations. A network of stations on the moon could demonstrate what's possible with multi-station planetary seismology, developing techniques and software that could eventually be applied to Mars, Europa, Titan, and other worlds. There's also the possibility of detecting impacts in real time. The moon is constantly being hit by small meteorites. A global seismic network would detect these impacts, measuring their size and energy, combined with optical observations of the impact flashes. This data would improve our understanding of the meteorite flux in the Earth-Moon system, which has implications for both lunar safety and our understanding of impact hazards to Earth. Now let's talk about one of the most elegant experiments already running on the moon, and why expanding it could push the boundaries of fundamental physics. When the Apollo astronauts visited the moon, they left behind retroreflectors, arrays of precisely angled mirrors designed to reflect laser light directly back to its source. Since then, observatories on Earth have been firing lasers at these reflectors and measuring the time it takes for the light to return. This experiment, called lunar laser ranging, has been running continuously for over 5 decades. It measures the distance between Earth and the moon with a precision of about 1 millimeter. 1 millimeter across a distance of 384,000 kilometers. That's a precision of about 3 parts per trillion. And this extraordinary measurement has been used to test fundamental physics in remarkable ways. Lunar laser ranging has confirmed that the moon's orbit agrees with general relativity to extraordinary precision. It has tested the equivalence principle, the idea that all objects fall at the same rate, regardless of their composition, using the Earth-Moon system as a giant laboratory. If the equivalence principle were violated even slightly, the moon's orbit would be measurably different from what general relativity predicts. The fact that it matches confirms the equivalence principle to a precision of better than 1 part in 10 trillion. The experiment has also measured the rate at which the moon is receding from Earth, about 3.8 centimeters per year. It has detected the gravitational effects of the sun on the Earth-Moon system with extraordinary precision. It has placed constraints on hypothetical modifications to gravity that some physicists have proposed as alternatives to dark matter. But the current retroreflectors are degrading. Decades of micrometeorite impacts have pitted their surfaces, reducing the number of photons that return to Earth. The signal has weakened considerably since the Apollo era. New retroreflectors, with improved designs and larger collection areas, would dramatically improve the precision of these measurements. Next-generation retroreflectors combined with improved lasers on Earth could push distance measurements to sub-millimeter precision. At that level of accuracy, entirely new physical effects become detectable. We could test general relativity in ways that have never been possible before. We could search for deviations from Einstein's predictions that might point toward new physics, toward a theory of quantum gravity that unifies general relativity with quantum mechanics. This is one of the holy grails of modern physics, and the moon offers a unique platform for testing it. There's also the potential for gravitational wave detection on the moon. Gravitational waves, ripples in spacetime caused by massive cosmic events like merging black holes and neutron stars, were first detected in 2015 by the LIGO Observatory on Earth. LIGO uses laser interferometry, measuring tiny changes in the distance between mirrors separated by 4 kilometers. The moon's seismically quiet surface and vacuum environment could potentially host a gravitational wave detector that operates at different frequencies than Earth-based detectors, opening up new windows on the gravitational wave spectrum. Let me step back and look at the full picture, because the range of science that the moon enables is almost absurd in its breadth. Radio astronomy that can only be done from the far side. Biological research on partial gravity that can only be done on the surface. Radiation studies that can only be done outside a magnetosphere. Seismology that requires a global network of surface stations. Fundamental physics tests that require precise laser ranging over cosmic distances. Material science that requires a vacuum across scales impossible on Earth. Each of these requires conditions that exist on the moon and nowhere else that's accessible. And there's a crucial point that ties all of these together. None of this science can be done from orbit. You can't do radio astronomy from lunar orbit because you periodically pass above the near side where Earth's radio noise is visible. You can't study partial gravity biology in orbit because orbit provides microgravity, not partial gravity. You can't do surface seismology from orbit. You can't test radiation shielding effectiveness from orbit in the same way you can on the surface. You can't anchor retroreflectors in orbit. The science requires being on the moon, on the surface, with instruments planted in the ground and experiments exposed to the actual lunar environment. The moon isn't just a place to visit. It's a platform for discovery across nearly every branch of physical science. It offers conditions that exist nowhere else within our reach. And the experiments that can be performed there have the potential to answer fundamental questions about the universe, about physics, about the viability of human life beyond Earth. Questions that we cannot answer from any other location. The moon has been sitting in our sky for as long as the Earth has existed, quietly offering the darkest skies, the deepest vacuum, the most radiation-exposed surface, and the only partial gravity environment accessible to humanity. All we have to do is go there and use it. But science alone doesn't justify building permanent infrastructure on the moon. For that, you need something more practical. You need resources. You need the ability to live off the land, to extract what you need from the world beneath your feet, to turn dead rock into fuel and oxygen and shelter. And it turns out the moon has exactly what we need. We just had to learn how to find it. The orbital mechanics, the ancient geological archive, the scientific laboratory, all of it matters. But there's one more piece to this puzzle that ties everything together. One more reason we're going back to the moon that transforms it from a place we visit into a place we stay. A place we build. A place that becomes the foundation for everything humanity does in space from this point forward. The moon has resources. Not the kind of resources that seem impressive on a brochure, but turn out to be useless in practice. Real, tangible, extractable resources that solve the single biggest problem in all of space exploration. the problem of weight. Here's the fundamental economic reality of spaceflight that most people don't fully appreciate. Everything we send into space has to be launched from Earth's surface. Every kilogram of food, every liter of water, every piece of equipment, every bolt and wire and panel, all of it has to be loaded onto a rocket and hurled through the atmosphere at 25,000 miles per hour. And that costs money. Enormous amounts of money. As of the mid-2020s, launching a single kilogram into low Earth orbit costs somewhere between $1,500 and $5,000, depending on the rocket. That's just to orbit. Roughly 300 kilometers above the surface. Getting that kilogram to the moon costs significantly more. Getting it to Mars costs even more than that. And the costs multiply quickly when you consider how much material a permanent outpost needs. A single astronaut on the International Space Station requires about 3.6 kilograms of supplies per day. Food, water, oxygen, and other consumables. For a crew of 4 on the moon, that's about 14.4 kilograms per day. Over the course of a year, that's 5,256 kilograms of supplies, not counting equipment, spare parts, habitat maintenance materials, scientific instruments, or anything else. Just the consumables to keep 4 people alive. At current launch costs, just the supplies to sustain 4 humans on the moon for a year would cost tens of millions of dollars to deliver, and that's being optimistic. For a permanent base with rotating crews and expanding capabilities, the costs become staggering. Billions of dollars just to ship the basics. This is why living off the land isn't a luxury for lunar settlement. It's a necessity. It's the difference between a permanent base and a temporary camp. And it's why the discovery of water ice at the moon's poles changed everything. For decades, scientists debated whether water existed on the moon. The Apollo samples were bone dry. The lunar surface, baked by solar radiation and exposed to the vacuum of space, seemed like the last place you'd find water. Any water molecules on the surface would be blasted apart by ultraviolet radiation, or ejected into space by the solar wind. The moon seemed completely, utterly desiccated. But there was a theoretical possibility that tantalized scientists. The moon's axis of rotation is tilted only about 1.5 degrees relative to the plane of its orbit around the sun. This is a very small tilt. Earth's axis is tilted about 23.5 degrees, which is what gives us seasons. The moon's nearly upright orientation means that sunlight always comes in at a very low angle near the poles, and in deep craters near the poles, the crater walls are high enough to permanently block sunlight from reaching the crater floor. These are called permanently shadowed regions. Some of them haven't seen a single photon of sunlight in billions of years. The temperatures in these regions are astonishingly low, dropping to about 40 Kelvin, which is roughly minus 233 degrees Celsius. That's colder than the surface of Pluto. At these temperatures, water molecules that wander into these craters from any source, cometary impacts, volcanic outgassing, solar wind interactions with surface minerals, become trapped. They freeze instantly and cannot escape because there's no energy to liberate them. Over billions of years, these cold traps have been accumulating water ice molecule by molecule. In 1998, NASA's Lunar Prospector mission detected elevated levels of hydrogen at the moon's poles using a neutron spectrometer. Hydrogen is a key component of water, and its concentration near the poles strongly suggested the presence of water ice. In 2009, NASA's LCROSS mission deliberately crashed a spent rocket stage into a permanently shadowed crater called Cabeus near the South Pole. A trailing spacecraft flew through the debris plume and analyzed its composition. The results were definitive. The plume contained water, not just traces, significant amounts. The regolith in Cabeus crater was estimated to contain about 5.6% water by mass. Subsequent observations from India's Chandrayaan-1 orbiter, NASA's Lunar Reconnaissance Orbiter, and other spacecraft have confirmed that water ice exists in permanently shadowed craters at both the North and South Poles. Estimates of the total amount of water vary widely because we haven't directly sampled most of these deposits. Conservative estimates suggest hundreds of millions of metric tons. More optimistic estimates suggest billions of metric tons. Even the conservative figures represent an enormous resource. And water on the moon isn't just water. It's everything. Water is made of hydrogen and oxygen. 2 hydrogen atoms bonded to 1 oxygen atom. With electricity, which can be generated by solar panels, you can split water into its component elements through a process called electrolysis. The oxygen becomes breathable air, one of the most basic requirements for human survival, generated from ice mined on the moon. No need to ship it from Earth, no need to carry tanks of compressed gas on rockets. Just extract ice, melt it, and split it. But here's where it gets truly transformative. Hydrogen and oxygen aren't just life support consumables, they're rocket propellant. Liquid hydrogen and liquid oxygen are one of the most efficient chemical rocket propellant combinations known. It's what the space shuttle main engines burned. It's what the upper stages of many modern rockets use. It delivers high specific impulse, which is the rocket science term for fuel efficiency. If you can manufacture liquid hydrogen and liquid oxygen on the moon, you can make rocket fuel on the moon. And if you can make rocket fuel on the moon, you fundamentally change the economics of every mission that goes beyond low Earth orbit. Remember the tyranny of the rocket equation. Every kilogram of fuel you carry requires more fuel to lift it, which requires more fuel to lift that fuel, and so on exponentially. For a mission to Mars, a huge fraction of the spacecraft's total mass is propellant. If that propellant could be manufactured on the moon and loaded onto spacecraft at a lunar fuel depot, the spacecraft leaving Earth would only need to carry enough fuel to reach the moon. The rest would be sourced locally. The mass that needs to be launched from Earth's surface drops dramatically. The cost drops dramatically. The missions become more achievable. This concept is called in situ resource utilization, or ISRU. It's been a theoretical pillar of space exploration planning for decades. But the confirmed presence of water ice at the lunar poles has transformed it from theory into engineering reality. The resources are there. The chemistry is understood. The technology to extract and process them is within our current capabilities. What's needed is the infrastructure to do it at scale. But water ice isn't the only resource the moon offers. Let's talk about the regolith itself, because that grey powder covering the lunar surface turns out to be remarkably useful. Lunar regolith is composed primarily of mineral oxides: silicon dioxide, aluminum oxide, calcium oxide, iron oxide, magnesium oxide. titanium dioxide. The exact composition varies by location, but across the entire Moon. The regolith is roughly 42% oxygen by weight. Oxygen is the single most abundant element in the lunar soil. It's locked up in chemical bonds with silicon, aluminum, iron, and other metals, but it can be liberated through various extraction processes. One method involves heating the regolith to high temperatures in the presence of hydrogen gas. The hydrogen reacts with the metal oxides, pulling the oxygen away from the metals and forming water. The water can then be electrolyzed to separate the hydrogen and oxygen. The hydrogen is recycled back into the process, and the oxygen is collected. The byproduct is pure metal, iron, aluminum, titanium, whatever was bonded to the oxygen. So this single process produces both breathable oxygen and useful metals from raw lunar dirt. Another method involves molten salt electrolysis, where regolith is dissolved in a molten salt bath and an electric current is passed through it. The oxygen migrates to one electrode and the metals to the other. This process has been demonstrated in laboratories on Earth using simulated lunar regolith, and it works. The metals extracted from regolith have obvious applications. Iron and aluminum can be used for construction. Titanium is strong, lightweight, and corrosion resistant. Silicon can be used to manufacture solar cells, providing the electrical power needed to run all these extraction processes. The Moon contains the raw materials for a self-sustaining industrial ecosystem. The regolith itself can be used directly as a construction material. It can be sintered, meaning heated until the particles fuse together without fully melting, to create bricks and structural blocks. It can be melted into glass or ceramic. It can be used as the feedstock for three-dimensional printing, building habitats and structures layer by layer using robotic printers. Several research groups and space agencies have demonstrated three-dimensional printing with simulated lunar regolith. The resulting structures are strong, radiation resistant, and can be produced in virtually any shape. This matters because one of the biggest expenses in building a lunar base would be launching construction materials from Earth. Every wall panel, every structural beam, every radiation shield launched from Earth costs thousands of dollars per kilogram. But if you can make these components from lunar regolith, processed and printed on site by autonomous robots, the cost equation changes entirely. You launch the robots and the processing equipment once. After that, the construction material is free. It's just sitting on the ground everywhere, in unlimited supply. Regolith also provides excellent radiation shielding. As we've seen, the lunar surface is exposed to the full spectrum of space radiation, galactic cosmic rays, solar particle events, all of it. Habitats on the Moon will need protection, and the simplest, most effective approach is to bury them under several meters of regolith. The regolith absorbs and blocks most incoming radiation, including galactic cosmic rays and solar particle events. No exotic materials needed. No heavy shielding launched from Earth. Just pile up the local dirt. A habitat buried under 2 to 3 meters of regolith would provide radiation protection comparable to being on Earth's surface. Now let's talk about something that sounds like science fiction, but is grounded in real physics and real measurements. Helium-3. The solar wind, that constant stream of particles flowing outward from the sun, contains a rare isotope of helium called helium-3. On Earth, Helium-3 is extraordinarily rare because our atmosphere and magnetic field prevent solar wind particles from reaching the surface. But the Moon, with no atmosphere and no magnetic field, has been directly exposed to the solar wind for billions of years. Helium-3 particles have been implanting themselves in the lunar regolith grain by grain for as long as the Moon has existed. The concentration is low, roughly 4 to 15 parts per billion by mass depending on location. That doesn't sound like much, and it isn't much per kilogram of soil, but spread across the entire Moon, the total amount is estimated about 1 million metric tons. Why does this matter? Because helium-3 is a potential fuel for nuclear fusion reactors. Not the conventional deuterium-tritium fusion that most current research focuses on, but a more advanced reaction called deuterium-helium-3 fusion. This reaction has a remarkable property. It produces almost no neutrons. Conventional fusion reactions release most of their energy as high-energy neutrons, which are difficult to contain and which cause radiation damage to reactor components. Deuterium-helium-3 fusion releases its energy primarily as charged particles, protons, which can be directly converted to electricity using electromagnetic fields. No steam turbines, no heat exchangers. Direct conversion of nuclear energy to electrical power with theoretical efficiencies far exceeding any current power generation technology. Now, I should be honest here. We don't have working fusion reactors yet, let alone the more advanced deuterium-helium-3 variety. Fusion power has been perpetually 20 years away for the past 60 years, but the physics is real. The reaction works. It's been demonstrated in laboratories. What we lack is the engineering to sustain it at scale. And the progress in fusion research has been accelerating, with several experimental reactors expected to demonstrate net energy gain within the coming decades. If fusion power becomes practical, helium-3 from the Moon could become one of the most valuable commodities in the solar system. A single cargo load of helium-3, perhaps a few hundred kilograms, could power a city for a year. The energy density is extraordinary, and the Moon has been stockpiling it for longer than life has existed on Earth. This is a long-term prospect, not an immediate one, but it illustrates a broader point about lunar resources. The Moon contains materials that may become invaluable as our technology advances. Water ice is immediately useful. Oxygen extraction is immediately useful. Metal production is immediately useful. Helium-3 might become useful within decades. And there might be resources and applications we haven't even imagined yet, waiting to be discovered as we explore and understand the Moon more deeply. Let's zoom out now and think about what all these resources mean in practical terms for the future of space exploration. The single biggest barrier to reaching Mars with humans is not the distance. It's not the travel time. It's not even the radiation or the psychological challenges, though those are real. The biggest barrier is the sheer amount of material that needs to be launched from Earth's surface to support a crewed Mars mission. Current estimates for a minimal Mars mission, a crew of 4 to 6 with enough supplies and equipment for a surface stay of about 500 days, put the total mass in low Earth orbit at somewhere between 500 and 1,000 metric tons. At current launch costs, just getting that mass to orbit would cost billions of dollars before the mission even leaves for Mars. But what if a significant fraction of that mass didn't have to come from Earth? What if the fuel for the Trans-Mars injection burn, the maneuver that sends the spacecraft from Earth orbit toward Mars, was manufactured on the Moon and delivered to a fuel depot at the Earth-Moon L1 Lagrange point? What if the water, oxygen, and radiation shielding were also sourced from lunar resources? The mass that needs to be launched from Earth could be cut by half or more. The mission becomes dramatically more affordable. More missions become possible. A sustained program of Mars exploration, not just one or two flag-planting expeditions, becomes economically viable, and this applies to more than just Mars. Missions to the asteroid belt, where valuable resources like platinum group metals and rare Earth elements exist in quantities that dwarf anything on Earth, could be fueled and supplied from the Moon. Missions to the outer solar system, to the moons of Jupiter and Saturn where subsurface oceans might harbor life, could stage from lunar facilities. The Moon becomes not just a destination but a supply chain, a logistics hub, a shipyard. There's another dimension to this that's often overlooked. The Moon is a proving ground. Every technology that humanity needs for Mars, for the asteroid belt, for deep space exploration can be tested on the Moon first. And the Moon offers something that no other testing environment can match. It's real, but it's close. Building a habitat on Mars means assembling structures in a hostile environment 9 months from Earth. If the 3-dimensional printer breaks down, if the regolith processing system doesn't work as expected, if the power generation falls short, there's no quick fix. Resupply from Earth takes the better part of a year. Help is impossibly far away. Building a habitat on the Moon means assembling structures in a hostile environment, close enough to Earth for a rescue mission. If something breaks, spare parts can be sent within a week. If a design fails, engineers on Earth can iterate and send a replacement in days or weeks, rather than years. If a crewed mission encounters a medical emergency, evacuation to Earth takes 3 days rather than 9 months. The Moon allows for rapid iteration. Build, test, fail, fix, rebuild, test again. This cycle, which is the foundation of all engineering progress, can run 10 times faster on the Moon than on Mars, simply because of the proximity. Technologies proven on the Moon can then be deployed on Mars with far greater confidence. Habitat designs, life support systems, resource extraction equipment, power generation systems, radiation shielding approaches, spacesuit designs, rover designs, communication systems. All of it can be developed and validated on the Moon in conditions that are genuinely harsh, genuinely representative of deep space challenges, but close enough to Earth to be survivable when things go wrong. And things will go wrong. They always do. There's a beautiful analogy here. Crossing an ocean in the age of sail required extensive preparation. Ships had to be built, crews had to be trained, navigation techniques had to be developed, supply chains had to be established. But before anyone could cross an ocean, they first had to learn to sail. They learned in harbors, then along coastlines, then across short stretches of open water. Each step built capability, confidence, and infrastructure for the next. Nobody sailed directly from a river to the open Atlantic. They worked up to it in stages. The Moon is our harbor. It's where we learn to live off the land in space, where we learn to build with local materials, where we learn to manufacture fuel from ice and oxygen from rock. where we learn what partial gravity does to the human body, where we learn how to shield against radiation, where we learn how to maintain complex systems far from Earth. Every lesson learned on the moon makes Mars more achievable, and everything beyond Mars more imaginable. Some people argue that we should skip the moon and go directly to Mars, that the moon is a distraction, a detour that wastes time and resources. But this argument misunderstands what the moon actually is in the architecture of human space exploration. Going to Mars without first developing lunar capabilities is like trying to build a skyscraper without first learning to pour a foundation. You might get lucky, but the odds are much better if you master the basics first in an environment where mistakes don't automatically mean death. Let me paint a picture of what the next few decades could look like if we get this right. First, robotic missions survey the permanently shadowed craters at the lunar South Pole, mapping the distribution and concentration of water ice in detail. These missions identify the best sites for extraction, the places where the ice is most concentrated and most accessible. Next, ICE, autonomous extraction systems, are deployed. Robots that can mine ice from the regolith, melt it, purify it, and store it. Solar-powered electrolysis units split the water into hydrogen and oxygen. Storage facilities keep the hydrogen and oxygen in liquid form, ready for use. Simultaneously, regolith processing systems begin producing construction materials. Three-dimensional printers build landing pads, roads, and radiation-shielded habitat foundations. The first infrastructure is built entirely by robots before any human sets foot on the surface. Then, the first crews arrive. Not for a 3-day visit like Apollo, but for stays of months. They live in habitats partially constructed from lunar materials and partially shipped from Earth. They conduct science. They maintain and expand the robotic systems. They test technologies. They learn what works and what doesn't. And they start to build. Over time, the base grows. More habitats, more processing equipment, more power generation. A fuel depot takes shape, first supplying missions returning to Earth, then supplying missions heading deeper into the solar system. The base becomes self-sustaining in water, oxygen, and basic construction materials. The amount of material that needs to be shipped from Earth steadily decreases. Eventually, the lunar base becomes a true settlement. Not just an outpost where people visit, but a place where people live and work for extended periods. A place with its own economy based on fuel production, material processing, and scientific research. A place that exports propellant to spacecraft heading to Mars and beyond. And then, from this foundation, humanity reaches for Mars, not in a desperate sprint like Apollo was for the moon, but in a sustained campaign supported by lunar infrastructure, spacecraft fueled by lunar propellant, crews trained by lunar experience, technologies proven by lunar testing. The moon doesn't replace Mars as a destination. It makes Mars achievable in a way it simply isn't without lunar support. This is the real reason we're going back to the moon. Not nostalgia, not politics, not national pride, though those things play their roles. The real reason is physics. The real reason is geology. The real reason is the unique combination of location, gravity, resources, and scientific opportunity that makes the moon the single most valuable piece of real estate in the solar system for a civilization that wants to expand beyond its home world. The moon has been orbiting Earth since before life existed on this planet. It's been recording the history of the solar system in its rocks. It's been collecting helium-3 in its soil. It's been accumulating water ice in its polar shadows. It's been offering the deepest vacuum, the quietest skies, and the most accessible low-gravity surface in our cosmic neighborhood. For all of human history, we looked up at it and saw a light in the sky, a companion in the darkness, a source of myths, stories, and wonder. Then, for a brief moment in the 1960s and 70s, we went there and came back, and for 50 years after that, we didn't return. But now we understand what the moon actually is. Not just a companion in the sky. Not just a place to plant a flag. It's a gravitational stepping stone that sits at the edge of Earth's deepest gravity well. It's a 4.5 billion year old archive preserving the history that Earth destroyed. It's a scientific laboratory with conditions that exist nowhere else within our reach. And it's a resource depot containing everything we need to fuel, supply, and sustain missions to the rest of the solar system. The moon isn't a destination. It never was. It's a beginning. The place where humanity stops being a species that lives on one planet and starts being a species that lives in space. Every plan for reaching Mars, for mining asteroids, for exploring the outer solar system, for building a future among the stars, every single one of those plans works better, works cheaper, and works sooner with the moon as a foundation. We're going back to the moon because the moon is where physics wants us to go. Because 4.5 billion years of untouched history are waiting to be read. Because experiments that will reshape our understanding of the universe can only be performed there. And because the ice in its shadows and the oxygen in its soil are the keys that unlock the rest of the solar system. The moon has been waiting, patiently, silently, since before life existed on this planet. And we're finally ready to use what it's been offering us all along. Thank you for joining me on this journey tonight. And the next time you look up at the moon, remember what you've learned. That familiar light in the sky isn't just a dead rock. It's the most important stepping stone humanity has. And we're about to step on it again. Not to visit, to stay. Good night, and keep looking up.